Okay, so it's my pleasure to introduce Cyrill Stachniss. He's a professor at the University of Bonn. Heads the lab for the photogrammetry and robotics lab. He received his PhD from the University of Freiburg, and he was an associative editor of the IEEE Transactional Robotics and a senior editor of the IEEE Robotics and Automation letters. Then he received the IEEE RAS Early Career Award, and his research is widely recognized, and it received several Best Paper Awards at ICRA and IRAS. He is currently also one of the spokespersons of the DFG Cluster of Excellence, PhenoRob, which deals with robotics and phenotyping for sustainable crop production. And his central areas of research are solutions to simultaneous localization and mapping, visual perception, robot learning, self-driving cars, agricultural robotics, and unmanned aerial vehicles. And after the short introduction, the stage is yours. Thank you.
Okay, perfect. Thank you very much. I'm here to entertain you for the next 25 minutes, and I want to talk to you about environment monitoring and intervention for robots in agriculture and provide you with a few examples of why I think this is an important topic to work on, what are current open issues, and show you some of the work that we have been doing in the past. So first of all, the most important question is, why should you care? So why is it a problem or relevant problem to address using robots or digital technologies in agriculture and especially crop productions? That's what I'm looking into here today. And there's one single slide which I typically use now to motivate my presentations on this topic. And this is if we look to the amount of biomass that we need to produce between 2010 and 2050, so within 40 years, 10 years already passed, this is approximately the same amount of biomass that had been produced from the beginning of mankind until 2010. So what we need to produce in 40 years is the same that we have done from the beginning of mankind until 2010. And as an additional constraint, we need to produce this biomass in a sustainable manner. That means that also the next generations should have the chance to produce enough biomass. And that's actually a serious challenge and something that we have to address. And the reason for this increased biomass that needs to be used is has multiple reasons. This is food, we want to eat something, feed, we need to feed our animals, fuel, so we don't only put the fuel that we put in our cars also has a certain amount that stems from crops, and we are using more and more fuel, so this is something we need to take into account as well as fiber. At the same point in time, we not only need to produce more biomass, we also see a substantial loss in biodiversity. And so this is one study ranging over nearly 30 years in Germany, looking into the amount of flying insects in protected areas in Germany, so natural reserve areas. And we can even see here that within the last 30 years, we lost around 3/4 of the flying biomass in terms of insects. And one of the reasons, probably not the only reason, but one of the reasons is the use of pesticides and agrochemicals in agriculture that has reduced the amount of flying insects out there. So if we look into the central challenges that crop production is facing today, on the one hand side, we have this demand for a high yield I was talking about. At the same point in time, we have limited arable land and natural resources. That means we cannot simply scale up the amount of land that we use in order to grow our crops. We are still using a massive amount of agrochemicals, although the development is very country dependent. But still, a lot of agrochemicals are used today, and this has negative side effects onto our agro-ecosystem. In addition to that, climate change also poses several challenges to us. So depending on the area where you live, climate change can be seen as something which is positive, at least for crop production, or something negative. But one of the things which is definitely the case that we need to adapt quicker to the change in the climate. That means kind of 50 years ago, the breeding companies were faster in breeding new crop varieties, for example, to increase yield or to make them resistant against certain stresses. And climate change has changed that in the sense that climate change is now faster then the breeding companies generate new varieties of plants. And this has led to a stop in the increase in yield that we see, for example. So we want to boil all these challenges down to a single question. Then this question would be, how can we reduce the negative impact of crop production on our ecosystem, and at the same point in time address the demand for a higher yield or for an increased yield? And these are kind of two things which can work opposite to each other. And how can we balance this? How can we reduce negative impact and increase yield at the same point in time? And the way we can do this, actually, we have two key levers that we have in our hands. Let's first look to increased yield. What can we do to increase yield? And here we have to distinguish between kind of the actual yield and the potential yield. So potential yield is something that we can generate if everything is in perfect conditions, and actual yield is what we actually generate, for example, due to plant diseases or weeds that we see in our fields. And we can see we basically have two levers at hand that we can use in order to push the actual yield and also potential yield upwards. This is first breeding technology, and the second thing is crop management. So breeding here means generating new varieties of plants, which, for example, produce a higher yield or which are more resistant against certain stresses. And management is performing the actions on the field in order to optimize the management, for example, doing active weed control or spraying herbicides. These are things which we refer to here as management or field management. So we can use breeding and management in order to kind of push the yield upwards. But breeding and management are also two tools that we can use in order to reduce the impacts or the inputs, sorry. And inputs here are fertilizers, agrochemicals that we use in our fields. And if we reduce the number of inputs in our fields, this is potentially positive for our impact on the agroecosystem. So this is not equivalent to reducing the negative impact on the agroecosystem, but it's a key player, the inputs that we put into our environment. And again, breeding and management can also help us here to reduce the inputs and thus reduce the negative impacts on our agroecosystem. And this is the central question, and these two, how can we play with those two levers that we are tackling in our cluster of excellence PhenoRob at the University of Bonn, where we're looking into robotics and phenotyping for sustainable crop production. And we basically have three pillars of research in here. And the first one is, and this is the one which is also related to this event in here, and this is also the area where I'm personally working in a lot, and this is developing digital technologies for supporting operations on the field. This could be UAVs that monitor the environment. This could be mobile robots driving over the field doing intervention actions. This could be analyzing data from a mobile phone on the field in order to assess the status. And here, sensing technologies, robotics, and machine learning plays an important role. Besides this, we also need to increase our understanding of plant and soil. This is also, for example, important if we think about supporting breeding companies. So how can we provide them with the relevant information that allows breeding companies to faster assess the performance or potential performance of varieties on the field? So phenotyping plays a very important role here. And this happens above the soil, so on the plant that we see with our human eye, but also inside the soil in terms of root growth and interactions of soil and root, for example. Last but not least, we need to kind of scale things up and integrate these findings into the environment and also into economy, because it doesn't help us if we just can build cool tools or cool robots which can solve some of those aspects, but they are too expensive to operate in our fields or can't be scaled up. So making this economically viable and upscalable is an important aspect here if we really want to make change for society. And I want to look today into a small subset of what we are doing here in this cluster. And I want to look into the question how robotic monitoring and intervention can help us towards sustainable crop production. And so monitoring and intervention are two tasks in here. Monitoring refers to knowing what's going on the field. So we need to get an understanding what's the current status on the field, what's happening, what should we do? And once we have assessed the status quo, and then we need to do the right thing, so performing the correct intervention action. And I want to start with monitoring and then throughout my talk, look into intervention and give you examples where we can use the technology that we have been developing as a community, looking into machine learning, into pattern recognition, into robotics, in order to make a contribution here to that field. So I want to start with monitoring, and the easiest way to monitor a field is typically a UAV. So we can fly with a UAV over fields, use, for example, camera data that we record over the fields in order to analyze what's going on. What you see here on this image is a standard DJI Phantom 4 drone with its out-of-the-box camera. So a drone costing in the order of $1,000 to $1,500 US dollars, flying over sugar beet fields here in Kleinandorf, one of our test farms, observing the field and assessing the status quo. So we need to interpret our camera data and build models of the environment in order to assess the status quo. And this is something that, a problem that we know, which we typically refer to as semantic scene interpretation or scene understanding, semantic segmentation, typically combined with some geometric estimation techniques. This could be bundle adjustment, this could be SLAM, basically that the name that you're using depends a bit on the community you're stemming from and which sensors you're precisely using. But overall, that's a type of problem that, or the type of solution that we can actually take in order to tackle that challenge. So let's start with semantic segmentation. So we get an image from a field, this one, for example, taken from a ground robot, but more or less the same as for a UAV. And what we want to do is we want to turn this image into a semantically segmented image that tells us what we precisely see on the field. So for every pixel, we want to assign a label, for example, saying this is a sugar beet plant, so our value crop in this example, or another pixel refers to a weed or to a background. How can we make this translation of turning this image into this semantically segmented image? And a standard approach to do this is to use a semantic segmentation CNN, several of those networks that we find out there, where on the left-hand side, we put in our input image, so our camera data with the different channels, and want to turn this into an output image. And that's something that we as a community have been doing for quite a while. We use this, for example, in the context of autonomous driving in order to parse the scene and estimate which of the elements or objects that we've seen are cars, pedestrians, sidewalks, road. So something we have been investigating since quite a while, or in the context of mobile robotics, for example, identifying which pixels we see in an image refer to humans, so that we can use this for human-robot interaction or for filtering out dynamics and mapping for different aspects. And if we bring this together, we can actually turn this data into images or into an orthophoto, or in this case, it's just an aerial image here, which is georeferenced, so that we know for every pixel what's the position of that pixel in the real world. And then we can analyze the status quo of the field. So in some areas, we may say, okay, there's a high weed pressure, we better execute some weed control. In other areas, everything looks fine. And maybe in a third area, the growth is fairly small. So we may want to target our fertilization actions to this area of small growth. And with this information, we can actually provide a management that is not field specific. That means that we are applying the same treatment of the whole field, but we can target that to individual aspects. So for example, doing only weed control in areas where it's needed. In this way, substantially reducing the amount of agrochemicals that we need in terms of herbicides. In other areas where everything is fine, we don't want to do anything. We don't even want to drive over the field in these areas because this would lead to additional soil compaction. And in other areas, we may want to apply fertilizer, for example. One of the challenges that we have in those systems from the image interpretation point of view is that typically the amount of training data that we have for these types of environments is substantially smaller compared to whatever, finding cat images on the internet or faces of humans, because there's simply a smaller number of plants or images of plants labeled that we can use out there. And thus we investigate a lot of techniques on how we can integrate background knowledge into this learning process in order to speed up learning and reduce the number of training examples that we need. And one of the things that we did, for example, was using kind of features that we, in the old days of machine learning, developed by hand or used existing features in order to, for example, learn whatever, a random forest for classification. We could use this information and provide those types of features that have proven to be useful in the past as a starting point for our networks, and in this way kind of push the network towards using good features that have been useful in the past, but then adapting those features over time so that with a small amount of training data, we actually get a similar performance and also have often better generalization capabilities. And it turns out with those fairly simple techniques, we can actually reduce the number of training data that we need by approximately a factor of 10, still achieving the same performance. Of course, in the long run, this effect will vanish because we will learn all the features from data, and that's fine. But especially if we have a small amount of training data available, this can be really helpful. And then we can actually apply this to different types of environments, for example, crop weed identification or finding barriers for vineyard operations or vineyard maintenance. So there's actually a large number of different applications which are out there for which we can actually use this type of techniques. This has also led to one of the spin-offs of our cluster of excellence, the company called Pheno-Inspect, which uses UAV data now with higher resolutions and kind of a bit more professionally in order to provide phenotyping using UAV data for breeding companies. And there are several problems that we can address here which are relevant for breeding companies. This could be emergence counting. So when happens an emergence for different plants, for different varieties. We can do weed mapping, we can do ear counting in wheat, trying to estimate yield fairly early in the process, and we can do all those analysis of breeding plot analysis in a non-destructive manner at large scale by just flying with the UAV out of the field and providing highly detailed analysis, which is really important for making the right decisions. And we can even go a step beyond just kind of this image-based semantic analysis. Still, old geometric estimation techniques really help us in order to perform phenotyping activities. And I brought a small example over here. This is a tomato plant scanned now in a laboratory environment with a high-resolution laser scanner compared to images at different days. And then we can see how the plant grows over time. And the question is, can we build kind of a full 40 plant model, estimating how the plant evolves over time, at which point in time certain events happen, like new leaves emerge, and so that we can actually perform a registration of those 3D data over time. And this is something that is kind of challenging if you look to the different type, how the same plant looks like at different points in time. And it's a form of kind of non-rigid registration. There also the topology changes. And that's something that people have been investigating since quite a while. So this is one work done by Dirk Hannon and Sebastian Thrum around 20 years ago, at this time using a mobile robot with a pan-tilt laser scanner in order to scan humans and then register images of moving humans in the environment using non-rigidity of the person. And of course, the topology of a person typically doesn't change, which we have here for the plants, but a lot of techniques that have been used in order to do a matching of human body and body shapes can also be used for plants. So one of the things that we can do is, for example, we can generate a skeletonization from the 3D point cloud data and perform the skeletons or compute the skeletons at different points in time, because it simplifies the data associations over time. And then we may want to put a bit more brain power in how to do those data associations, because the shape of the plant can actually change over time. And we, for example, looked into hidden Markov models for finding data association between this changing topology. And as a result of this, we can now kind of ignore the point cloud for the moment and only work on the skeleton and find data associations of those skeletons at different growth stages. And then we basically have a graph structure with constraints between those individual graphs, telling us something about the data association, then also how the plant has changed its appearance. And this is actually something which is very similar to a graph-based SLAM in dynamic environments and or bundle adjustment in changing environments. And a lot of techniques have been built in the robotics community to solve this problem. So this is an example of graph-based SLAM, actually work done by Jens Belay into 3D LiDAR-based mapping with an autonomous vehicle, showing here examples of the kitty data set, for example. And the techniques that sit behind those mapping approaches can also be used in the plant domain. For example, if you want to estimate the deformations, then we can actually look into different types of constraints that we may have used in graph-based SLAM. So compared to graph-based SLAM, where we only look into rigid body transformations in order to do the post-graph optimization, we have here different types of transformations. For example, we have affine transformation or locally affine transformations in order to express the possibility that the plant grows over time. We have certain constraints on the kind of rotation, that we don't have arbitrary rotation between two nearby points. We have constraints in terms of the correspondences in regularization terms, that we kind of assume that where the growth happens on a plant or on a leaf, for example. And with this, we can perform an optimization problem, which can be seen as an extension of the standard graph-based SLAM approach in order to perform this quality registration, so that we're able to perform registration of the plant over time, even if the appearance changes dramatically. And as a result of this, we can actually perform a registration over time. So what you see in here, so the 3D point clouds which fly through from the side are the actual measurements, and the red point cloud here is a measurement that we are computing or interpolating or extrapolating also between the growth, so that we can generate a virtual appearance of the plant at every point in time, and kind of synchronizes with the actual measurement that we got at different points in time. So we are actually able to track the growth of the plant over time and then estimate how individual organs of that plant grow. So we can provide, a really detailed analysis how the individual parts of the plant grow over time, and then track how different plants behave. And this can be important for breeding applications. We want to see how the development of a plant changes over time. And this, for example, allows us to make very early assessments on what will be the potential performance of this plant by extracting features in a non-subjective, so as objective as possible manner early in time, and come back to this data later when we see how the plant actually evolves. These were a few examples that I've been providing in terms of monitoring and understanding what's going on in our field, but we also need to do the right thing. Doing the right thing is less relevant for the breeding application, because here still the human breeder typically makes decisions. But that's different if we look into the management part, where we assess the status quo on the field and then derive automatic intervention actions that robot can actually execute. So we now want to look into doing the right thing, given that information that we have. And I want to go back again to one of my early examples with which I started, having this image taken from a ground vehicle of the field, and having a plant classification or a semantic segmentation system over here, which actually analyzes every pixel in the image and tells us what's going on. And once we have that information, we can actually decide, okay, we actually want to get rid of all those small red wheat pixels. So what can we do in order to eliminate the wheat in an as effective as possible manner? And the first thing that we have done in here, we have installed this plant classification system on an agricultural robot. This was the result here of a European project called Flourish, which was coordinated by Roland Siegwart from ETH Zurich. What you see in here is our plant classification system, which takes the downward-facing camera data and analyzes in real time what happens on the field, so that the robot is able to assess the status quo while driving over the field more or less in real time. And then we can actually execute weed control actions, for example, and eliminate the weed plant. And there are different ways how we can actually do this. The easiest form is just do a selective spraying and just spray the weed plants with our herbicide, and this way dramatically reduce the amount of herbicide that is needed on the field. By approximately, whatever, 80%, I can reduce the amount of herbicide that I'm using if I just spray the weed plant itself and not the whole field, which substantially reduces the impact on the agroecosystem. But I can even go a step further and do other techniques, such as manual weed removal. So this is an earlier version of the same robot using basically a stamping system in order to weed control. This was developed by Bosch, and you can see this is a glorified Bosch nail gun, which is able to kind of nail the weeds back into the ground. So if we can see which plant is a wheat and which plant is a sugar beet, we can leave the sugar beets in place and just nail the wheat plants back into the ground. And depending on what type of wheat we actually have, some can be stamped in this way, others not. So some we may want to spray. And so we can actually build a system which kind of learns how to treat which plant in which way. So grass weeds are better to be sprayed. Other plants we want to keep, like our sugar beet. Other weeds we want to stamp. For this, we need to have a precise stamp location. So it's a combination of geometric estimation technique and semantic estimation techniques, which play an important role in here. We can even go a step further and then use a laser in order to burn away wheat to do, again, a full chemical-free wheat control. And these were first experiments that we're doing in the context of the startup Escada Technologies, trying to bring wheat control into those fields. And there are, however, several challenges that we actually need to address if we kind of want to roll that out in larger environments. And one thing is the robustness to operate under varying conditions, especially field conditions. So if we train a classification system here in Bonn and then ship it to our partners in Renningen or in Zurich, then we can see that the appearance of the wheat, of the crop, of the soil itself changes so that the classification system will degrade in performance, at least to some degree. And so what you can see here is the kind of the training field A and test field B, and if the appearance is substantially different, the growth stage is different, it typically leads to low generalization performance, basically dropping down to whatever, only being able to recognize 80% of the plants correctly. And this is not good enough for doing this type of wheat control. So while those systems operate accurately in environments where the training and the target domain images look similar, the problem happens if you move to a new target domain where the appearance changes substantially. And in this case, the classification may be very, very bad. So one of the problems that we're looking into is domain adaptation, trying to translate images from one domain to another domain so that we can change the appearance so that we actually get correct classification results. So doing a translation from one environment to another environment. And so here are examples of training field and the conditions in the testing field, and ways how we can learn to translate images from one domain to another domain. So we can see here on the top right is one of those translated images. So making a training image look like an image as it comes from the test field, so that we can learn our classification system on those translated images and still have a very good performance. This is just one example of those challenges. There are several other challenges out there, which I don't want to go into the details, like using different robots, using different cameras, using different crops, different weeds. But still, there are a lot of challenges that need to be addressed where we have initial solutions, but for rolling it out on a large scale with very little human intervention, that's still challenging. In terms of weeding, we are quite far. It's still more challenging for the fertilization task because it's harder to assess the fertilization status of a field, or even crop protection, where we look into plant diseases are a challenge, because typically once we see the effect on the plant, it's already too late to do the intervention actions. And so there are a lot of open problems that we want to address here. My hope is that we see a lot of those agricultural robots that you see here on those images more often, doing more useful tasks in the field. And I think it's an important challenge that we can address as a society, and also gives us as a community, from robotics, from pattern recognition, from machine learning, to look into interesting new fields which can have a high impact. So from my point of view, monitoring intervention have potential to change agriculture if we use the technologies from robotics, from machine learning, from computer vision in here. A lot of the problems that we look into require a combination of technological expertise and agricultural expertise. So we need to talk to agricultural scientists or to crop scientists in order to understand what really the problems are that we need to be focusing on. And there's a large number of challenges out there. We only started addressing those. And the nice thing in here, it really makes an impact for our society. There's also a substantial amount of money in that field in agriculture, because it's so widespread that we can actually not only make important contributions here, but also earn money with the technologies that we are bringing here. And with this, I'm sorry for running 2 or 3 minutes late, but thank you very much for your attention, and I'm happy to answer questions that you may have. Thank you.
Thank you very much for this interesting talk, giving an overview of the challenges in intervention and monitoring of agricultural fields. So maybe I think we have one raised hand. Oh no, that's just applause. So do we have some questions from the audience? Maybe also. We have one question from the audience, so I can read it out. So have you considered any hilly areas
Currently we are using on the systems that we're using here, we have fairly flat areas, but we are looking also into vineyard maintenance. So we have built a small, it's not myself, but colleagues from the institute here have instrumented these small tractors that are used, for example, for vineyard maintenance and doing analysis of the yields. So there are several reasons why this is important. So in vineyard maintenance, you typically want to estimate what the expected yield will be, because due to legal regulations, if your yield is above a certain area for vineyard, you can sell your wine at a much lower price. So you're interested in actually doing pruning operations early so that you come as close as possible to the maximum yield you're allowed to get, but not overshoot. And for this, the prediction of the yield is fairly important. And for that, you can actually use instrument those tractors with the camera system and then simply count the grapes and berries that you see and estimate their size for doing a fairly precise yield analysis and then yield prediction for the operations in vineyards. So yes, it's absolutely possible. I personally have mainly worked in broad field agriculture, where at least here in the Bonn area, it's anyway a pretty flat area. We don't have too many mountains, but there's nothing in there which per se prevents the techniques from being used in more hilly areas, except that the navigation of the mobile vehicles is probably more challenging. But from the UAV perspective, when you do the monitoring tasks, this shouldn't be an issue at all from my point of view.
Thank you. So we have another question. How do you do the transition between the actual work in the machinery to a new robotized system? And second question, do you think that machines will be smaller than today, or maybe even use swarms?
Okay, so these are two questions. The first thing was, sorry, the first question was, again, sorry.
The transition from training the systems in
how the transition works. So there are different ways how you can achieve this. The first thing is, if you train especially neural networks with a small amount of training data, you're very likely to overfit to your field conditions. So what helped in the first place was putting this background knowledge into those systems of using features which have proven to be useful in the past, compute them kind of in closed form and providing them as additional inputs to the network. This helped to be able to generalize much better to new field environments. This is step number one. Step number two is if you want to allow for at least a minimum amount of labeling in a new environment, even if it's just a 1-minute labeling activity, you can exploit certain things better if you move to a new environment. For example, if you know that you are operating on a row crop field, you're steering the robot over a row for the first 5 meters, for example, based on the robot that can analyze which are the crops which are standing in a row, allows it to bootstrap the learning for this type of fields and can do an online learning approach and kind of let's say call it semi or self-supervised, mainly self-supervised fashion that you can adapt to the current field environments. Or we have been exploiting gun-based techniques in order to generate new images which look like images as they would be coming from the other field, even partially in an unsupervised fashion. And this actually works really well to do the transition. But again, there's still space for improvement. You can still, if you want to bring this to completely different types of crops, there are still a lot of challenges, and kind of the more we get to the close to 100% success rate, the better it is and the better form of assessment we can do. So there's still space for improvements. The second question was if we will have smaller machines. Most likely that will be possible. So if you have smaller machines, have different advantages. The first advantage is that they are more lightweight. So we lead to less soil compaction, which is one of the factors which reduces your yield, because if you're compressing the soil too much, nothing will grow there really well. The other advantage is that you can actually adapt to the environment. So you can actually use new field structures and also look into things like patch cropping or mixed cropping, where you plant different crops on the same field, which is much better from the biodiversity aspect. So depending on how we kind of reimburse farmers, for example, using different types of patterns of how they grow the crops on the field, giving them incentives to have an environment which is more biodiversity friendly, for example. Small machines can be a real game changer. Also, the thing is, if you think about multiple small robots, if you have a camera and spraying setup which just observe the part of the field, a small part of the field, if it's a big machine where we just need to replicate our camera multiple times or put the camera on smaller robots, smaller robots will be slightly more expensive, but they also have other advantages of redundancy, which we may exploit. So I think machines will become smaller. If we go all to kind of small scale machines of the size 20 by 20 centimeters, I probably have doubts about this, but we probably will have smaller devices than what we see today on our fields.
Okay, thank you. So I think we are running now too much into the coffee break, so maybe everyone needs some break in between. So I would suggest then to now make a 5 minutes coffee break.